Okay, thank you. So yes, indeed, yesterday the European Commission has published the proposal for a regulation of AI systems, and this was long expected. So in my talk today, I would like to give you some indications about how these systems work, how does AI actually work, and what does it mean to use AI. And also in a second part, some context about the genesis of this European legislative proposal to understand what are the foundations actually and why are we doing this at all. And doing this, I will also give you some excerpt from this legislation, which is quite, of course, new and needs to be analyzed more thoroughly, but just to give you some ideas about where it is going. Now, AI, actually, artificial intelligence, is today something which is quite present in our daily lives. And in this slide, I give you some examples of application domains, of sectors where AI systems are used. It is used in transportation. You know that people are working on so-called autonomous, I would say automated cars. It's used in logistics. It's used in security, healthcare, of course, image processing, for example, for detecting tumors. In assistance, some of these are, of course, experimental, but you have already chatbots interacting with people. You have social media and all the issue about influence, which goes into manipulation sometime. The use of AI systems for recruitment, for management of people, insurance in the finance sector as well, and the justice sector to help judges give a decision. And of course, it's also used in the military. So all these actually areas have a very important interest for us because it facilitates our lives. It makes things easier for us. This is what technology usually is for. But at the same time, it raises some issues. And I will try to explain this. Indeed, some of these applications are critical. And because of the nature of AI systems, we tend to delegate decisions to them. This is why AI systems are built to make computations. And we use these computations to make decisions. But sometimes it goes very far into the expectation that we have from the AI systems, and therefore we mostly have no choice but to accept their decisions or their recommendations. And there are critical applications such as healthcare or transportation, of course, or security. Critical means that any failure of the system could have catastrophic consequences. So this means that they have to be robust and safe. But there are also application areas that are challenging for human rights, values, equality, for example, surveillance, manipulation of opinion, policing, justice, access to jobs, access to education. And this is also something that requires governance and ethics. By governance, I mean not only regulation. It could be regulation, of course, but it means also governance within the institutions that develop, deploy, use AI systems. And to actually have this robustness and safety and to have this ethics and governance, we need that those systems are to be transparent and to be explainable. So I'll try to explain what this means. So in here, I'd like to go into more technical details. Actually, most current AI systems that are successful and used today are based on a technique which is called machine learning. And machine learning is based on using data, correlating data to make predictions about what future or new data are. So all the problem is to interpret some data, to make sense of some data, and the AI system will be built to search for regularities, similarities in the data that we don't see because they are very numerous, complex. For example, just pixels in images, and searching for those regularities in the data, and it's a large amount of data to detect those regularities and to make correlations, provides a means to interpret the data. This is opposed in a way to trying to reason on the data, to try to understand if humanly what the data is about, and to build general theories on the basis of which we can make predictions. Because in this case, if we have a theory, we can have a causal link, a causality between the data and the result, whereas the correlation ignore this causality. And this by itself is an issue with AI systems. So let me get into more detail. Those AI systems based on machine learning using a statistical data processing classification, which are very successful today. And they are successful because we have a lot of data to build the correlations, because there are a lot of data on the internet and it's accessible. And of course, because computing speed has increased a lot, and it increases, it doubles almost every 2 years. And this process, this method is now possible and efficient. So we use probability distributions, correlations to do that, and we use a technology, or I would say a method which is based on artificial neural nets, which can classify the data. And to do this, we use optimization algorithms. So these are the components. And the methodologies are either supervised learning. Supervised mean that the learning process, or training process, it should be called, is going to optimize some parameters to match a given answer. So this is why it's supervised. We, during the training phase, the learning phase, the correct answer for the classification is given to the system so it can optimize correctly. And then when it's used, it's going to be based on those training parameters. The unsupervised learning process is going to build classifications just looking for regularities in the data, assemble together data that look similar. And there is also another method which is called reinforcement learning that can be used also with other methods such as supervised or unsupervised. It's different. It's going to try to find out what is the best action, the best next action, based and using a reward signal, which is just providing a number actually about the value of an action, the utility of an action, and then the system is going to optimize the total reward. So to explain this a little bit more, I'm going to go into more detail, but just having a look on the legislation that has been published yesterday, the definition of artificial intelligence given by the Commission for this purpose is a software system that is using machine learning approaches, So this is what I just mentioned, but also more, I would say, symbolic and logic-based methods. So this is another aspect I will not develop today, but it's also a methodology using deductive, inductive logic, symbolic reasoning, expert systems, which nowadays are a little bit less successful because they are based on representations and logical representation. And here you have causality, but because of the fact that they are not based on a large amount of data that is just processed to find out the regularities, it's in a way less accurate. And also there are statistical approaches which are used widely and not just in artificial intelligence systems. Now, let's have a closer look on the AI systems that are based on machine learning and specifically on neural nets. So in this figure, I show a very, very simple neural net, 3 layers, the input layer and the output layer, and in between, the hidden layer. It's called hidden because it's between the input and the output. And when you speak about deep learning, it means you have many, many, many hidden layers. And the important thing here is that you have those units which are called neurons, and the neuron is just a computation unit. Mathematically, it's a function that is going to make a summation of its inputs, go through a function that is going to be computed based on this summation and provide an output. The training phase is about adjusting the synaptic weights, which are the parameters of the neural net, which are the parameters that give more or less importance to the inputs to provide a given output. And in supervised learning, you know what the output is. I will show an example in a minute. And you are going to optimize the synaptic weights, those W's in the figure, to adjust them to the correct value. Correct means that provides the expected outputs as much as possible. It's never 100%. And this is based on the process of optimization, which is called backpropagation of errors, to reduce those errors, the difference between the synaptic weights and the desired, so that the desired result is what we need. And the difficulty is that there are millions or billions of parameters, depending on the size of the network. So it's a very complex system. And of course, the result is that you cannot have any causal link between a given value of the synaptic weight, one of those billions of values, and the output. So the system is opaque. And this is why we speak about a black box when we speak about machine learning, because it is opaque, because you don't have this causality. So let me give you an example here to explain a little bit more about the parameters about an AI system for face detection. So typically, this system will take a lot of data. Data are images of faces, for example, here, and the faces are in a bunch of data, like thousands, hundreds of thousands of images with faces. And here I'm not recognizing individuals, I'm recognizing that there are faces in the image, just faces, not who are these people. So it's not facial recognition, it's facial detection. And this black box, I'm going to open it now to see how it provides its answers. Opening the black box, you see that I have a very simple system. It has 3 layers. The input layer is a process that computes from the image something called a gradient, which is just detecting contours of the images. And then we are going to search for some alignment of the pixels, horizontal, vertical, diagonal alignments. These alignments are going to be extracted by the system, and the adjustment of the synaptic weight, in this case, this is a convolutional network, which means the basic operation is a convolution, a mathematical operation between the within the images and between the images to find these alignments. And the system is going to be trained so that the synaptic weight provide more and more importance to some of those alignments, these alignments that we are looking for. And what are we looking for? This is defined here, for example, as looking for two horizontal alignments, which are separated but at the same level, it's an image, and another horizontal alignment of pixels, which is below and a little bit larger. And this means that what I defined as a face in this case is defined by the eyes, the two horizontal alignments, and the mouth. So this is what, for this system, a face means. Very, very simple definition of face, which is very reducing faces to only eyes and mouth. So you can fool the system very easily, but you don't know usually what is inside the system. So what influences the learning process is something that is decided and designed by the engineers, the people, the company who built the system. There are a lot of human decisions behind the system. Of course, there is the machine, the system decision, which detected a face, but this is based on the human design. What influences the learning system is first the data, and the data set has been selected by those people. So there is responsibility about detecting about this data set that has been decided to avoid bias, for example. If the system has been trained, for example, on faces of, say, white people, it means it will have difficulty to detect correctly the contours of faces for people who have dark faces. And when you give it an image of a person who has a dark face, a darker face, it will not detect a face, which is, of course, problematic and very inducing inequalities. So training tests and set tests and the labels. The design choices, how many layers do you have? What are the features you're looking for? The class semantics, what are eyes, what are mouth, what is a face in this case, and the optimization process itself. All this is under the responsibility of the designers. And this has limitations. Now, here, very quickly, I show you two different kinds of limitations of learning systems. Because they are not causal, because it's about correlation, it's very easy to correlate things that provide a very wrong answer. So these are examples from papers I'm mentioning, where a stop sign, for example, with some stickers on it, is mistakenly interpreted as speed limit 45. We're speaking about American stop signs and American speed limit signs, but the system has mistakenly interpreted this as speed limit 45. So imagine an automated car arriving to this stop sign and, of course, not stopping because it says speed limit. I mean, it sees it as speed limit 45. On the right, you have another problem where the position of the object in the image is results in a very different interpretation. For example, a motor scooter can be interpreted with a high accuracy, 99%, as a motor scooter, but you put it in a different position and it's interpreted with a high accuracy, actually 100%, as a parachute. So this yields to a need for robustness. The system is not robust. We need to ensure technology does the right thing, provides reliable results, and it's not the case. There is no solid verification and validation process with AI systems as there are in other computer-based systems. It's very difficult. It's a research topic, because of this complexity, the optimization process, and the components that are used. And we have no causal link, so we don't have any explanation about the results. And this is also a research topic. So my second part here, and I will go through it quite quickly because for the sake of time, is that this has yielded to several initiatives and decisions from organizations or governments about how to frame, how to legislate about AI systems. Here I'm showing the IEEE Global Initiative on Ethics of Autonomous System, basic autonomous and intelligent systems, basic proposal, which dates back, started in 2016, and 2019, the publication about ethically aligned design, which is based on pillars: universal human values, political self-determination and data agency, technical dependability, to provide identify some issues and provide recommendations to deal with that. And this has been published in a document which is accessible on the net called Ethically Aligned Design. But let us look on what happened in Europe, because we are in Europe, and this is what is going to be of interest for us, because a legislative framework is being defined. Is this trustworthy AI framework? So the European Union has asked a group of experts to give advice, to give opinion about ethical issues related to AI, and also recommendations about a policy about the investments that are needed for that. And on this, the European Commission has built its regulatory framework. What the high-level expert group came up with is that you need this technology to be trustworthy. And this is a prerequisite to develop, deploy, and use those systems. The trustworthiness is based on ethical principles. 4 ethical principles. First, the principle of autonomy, which means preserving human agency and control and oversight on the systems. Principle of non-maleficence, which means you don't develop systems to do harm or to exacerbate harm or to exacerbate safety issues. The principle of justice, fairness, equality, and the principle of explicability. Actually, the first 3 principles, you can find them in other domains, such as bioethics. But the principle of explainability is really, explicability is really for AI systems because of this black box, because of this complexity surrounding them. So we need transparency, we need traceability, auditability of those systems. So the expert group has come up with 7 key requirements for trustworthy AI. I'm not going to go through them, but you see for example, number 2 is technical robustness and safety. Number 4 is transparency and explainability. And number 7 is accountability. So this requires technical aspects because of this robustness issues. And it requires also non-technical aspects, including regulation, a framework for governance. And this is what the European Commission has come up with. But it has come up with a regulation based on something called a high-risk approach, a risk-based approach. And this is from this legislative proposal published yesterday. There are 2 main categories of high-risk AI systems, and the regulatory framework applies on high risk only. Systems intended to be used as safety components of products that are subject to third-party conformity assessment, or standalone systems which mainly with fundamental rights implications that are explicitly listed in an annex, which means a very specific list. And the high-risk systems and applications that are listed, there are 8 of them, and there are some details. I'm not going into the details for the sake of time, because I'm going to conclude now. It's based, for example, the issues that are considered high risk is biometric identification, critical infrastructure management, educational, vocational training, employment, private service access, law enforcement, migration management, administration of justice, and democratic processes. Now, I'm going to skip the slide to conclude with this about explainability. It's a little bit technical, but we need explainability to understand what the system are doing. And the main takeaways of my talk is that, yes, we need AI to bring efficiency to interpret data, but oversight is essential, especially in critical application. We have to adopt a human-centered approach, and this is what the Commission has adopted based on the 7 key requirements. We need certification auditing of AI systems to make them actually provenly compliant with some standards and certification processes. This governance and regulation framework is really necessary to adopt AI with trust. Thank you very much.